Evening, everybody. Tonight I want to show you things that are happening because of computer modeling and simulation, the effect it has on your lives, and where it might go in the future. So, as Ian said, I work at National Steel Car. I design freight cars. Even in such an old industry, modeling and simulation are major parts of the job and continue to drive the industry forward. And in some of the more advanced industries, or some of the newer industries, simulation is even bigger business. Just so we all agree what we're talking about, a model is, as stated here, is a thing that you can ask, it represents a thing such that you can ask questions about that thing. It's a very general term. It's not specific to computers. For example, an architectural model, you build a physical scaled model of a building that answers questions like, what's the building going to look like? A fashion model is a form of model as well, where a fashion model answers questions of, what's this clothing going to look like? Although, in the case of the fashion model, it's not really in their interest to answer that accurately. Simulation is just a model that evolves over time. It's as simple as that. So it's like watching the clothes sway on a fashion model. Frankly, I don't consider simulation to be too distinct from modeling, and I'm going to kind of talk about both today. Now, many simulations cover phenomena in physics. For example, there is this hilarious-looking horse simulator that I found on Wikipedia, World War I era of World War I. This ostensibly simulates what it's like to ride a horse. You sit on it, it moves back and forth, and it gives you that experience. Now, it may be an imperfect simulation, probably is an imperfect simulation, but it's been said many times that all models are wrong, but some of them are useful. Today I'm going to be focusing on computer modeling and simulation specifically. The underlying techniques of these, mathematical modeling and numerical approximation, are not anything new, but the power of modern computers has made them far more useful. The idea behind most of these is that you take a complicated phenomenon of physics and you break it into small chunks. Each of those chunks can be easily dealt with by a computer, and by breaking it into enough chunks that only a computer can actually handle, that computer can start to produce good results. So in my work as an engineer, I do a lot of multi-body dynamics. So I take a rail car, I break it into individual rigid masses, like are shown here. Each of those boxes represents some piece of the rail car. I make connections between those boxes, like springs and dampers. And I calculate, or I let the computer calculate the position of all those boxes every 100th of a second or so. This is the output of new cars, a rail industry-specific multi-body simulation software. And this is showing the dynamic curving test, a standard test, where the train goes around a curve, the tracks start going up and down. When it goes in and out, it's crazy. So we've got the train going around the curve now. And in a moment, it starts shaking violently back and forth. Tremendously exciting. No, okay, it's not tremendously exciting, but it's very important that I have done literally thousands of simulations much like this one over the course of my work, that I've been designing new suspension systems for trains, and in the process, I haven't had to build a single physical prototype to make it happen, to understand what is going on in those. All of these simulations have allowed me to design rail cars in a way that was unthinkable at the start of the rail industry. That back then everything was trial and error, you had some math to guide you, but you ultimately had to try it out before you could really understand what was going to happen. Now, we can look at something a little more colorful. This is a finite element model of a knee joint that I worked on for my master's thesis. This is the open knee. Finite element method works by taking a deformable body, breaking it up into a whole lot of cubes, or tetrahedra. You connect all of those squishy cubes together, and the way they move as as a whole tells you approximately how the piece itself would move. So here, it's evolved over calculated every 1/10 of a second. You can see that the stress appears in the mean. Finite element analysis can be used for many different problems, but I commonly use it for stress analysis and deflection. So you can see the bright red color at the center where the stress hits its peak from the two bones of the knee pressing against each other. Now this process is still in development, but this knee models like this could be used by physicians and surgeons to help understand the origins of certain injuries and degradations in the knee. Now if that's still not cool enough, we can go to a galaxy simulation. This work is by Ben Keller, a PhD student at McMaster University. And this is a Milky Way style galaxy evolved over 500 million years. Now, this visualization is nice. Finally, we've got a nice visualization, but this one's just for show, that the real results look a little more like this. In the top two boxes, we've got measurements of the density of gases, how much gas is concentrated in different areas. At the bottom, we've got the temperature of those gases in a slice through the center of the galaxy. These analyses are done with smooth particle hydrodynamics. That is, they take the interstellar gases as smooth lumps that slide gently past each other, and their gravity interacts, their temperatures interact. In these analyses, the time step is several hundred years long, a far cry from the fractions of a second of the earlier ones. Now, Ben's work specifically was on the effect of superbubbles. That's essentially clusters of supernova that all go off together, resulting in a giant gas bubble. Ben's work on incorporating these into the previous galaxy simulations has shown just how important they are for overall galaxy formation. Now, once you can simulate something accurately, there's an interesting thing you can do from an engineering design perspective. By simulating over and over, you can have your computer try different variations on that design and optimize it, that very quickly make it work excellently. This is a common test application. A beam is mounted on the left side and has a load applied at the right side, and you can see how it moves towards a shape that is stiff yet very light. Now, not all simulations nor all optimizations have to revolve around physics. There are simulations to analyze the timings of the traffic lights, the way groups of people exit buildings and emergencies, the way people board airplanes, the way parts flow through factories. All of these things have been simulated. All of these simulations have been used to optimize these processes. But I'll understand if you don't believe me about the traffic lights. By now, I think you're starting to see just how useful these techniques are in both science and engineering. Just think about product design. The prototyping stages can almost entirely disappear when you can instead do hundreds of simulated prototypes in far less time at far less cost. Simulation is one of those technologies that's enabling the rapid development of technology that we see today, particularly in things like yearly releases of new smartphones. But for all their societal importance, these engineering and science simulations don't look very cool. You might have noticed there's not a lot of effort put into cool graphics because these simulations are focused on being very accurate, but only in a very narrow domain. So for example, those railcar simulations I did earlier, they only work as long as the train is on the tracks. In cases where the situation gets cool enough that the train flies off the tracks, my simulations stop working. This is a different multi-body dynamics software, but it's doing a similar analysis. This train starts shaking violently back and forth, and in a few moments, you'll see the wheels lift off. There they go, and it stops. Because if we care about the car's performance, derailment counts as total failure. That once the train comes off the tracks, we have failed in our jobs as engineers. We don't care what happens result. This simulation can be used to further refine that suspension and make sure it doesn't fall off the tracks. But because it did here, I don't bother simulating it. So if you want to see some prettier pictures, we can go to the art world instead. But the obvious application of simulation in art is in video games. That lots of games incorporate some form of physics simulation. The important difference between video game simulation and the scientific ones we saw is that in the video games it must happen fast enough for the player to interact with it. To accomplish this, video games tend to crank down the accuracy on the simulations and use algorithms that are fast while representing reality only well enough to fool the player. Take this clip from Goat Simulator, for example. The goat headbutts the tank explodes, goat goes flying, the goat bounces off a tree, and the goat is almost hit by a car. I was disappointed that it didn't actually get hit by a car. And all of that makes sense. If you make a tank explode, you're going to go flying. But if you wanted to do this simulation accurately, the scientific way, it would end up looking a little more like this. Kind of disappointing. So in this one, we've applied some pressure to the inside of the tank, we've applied some forces to the outside of the tank, and the whole thing deforms until we have satisfied whatever regulations apply to this thing. We can see the tank deform, we can see the stresses appear in it, but we don't see it explode because that's well beyond our area of interest. If we wanted it to explode, we would have to add a whole lot of extra features to the simulation, and in most cases, we just want to make it not explode. Now, how does the game simulate this? Well, that goat's head, when it makes the headbutt, it has a box around it. That tank has another box around it. When the two boxes touch each other, explosion. That explosion appears in the sphere around the contact point, the goat is flung away. It's really simple. And the thing is, it works, it's fun. But that simulation doesn't tell us things like whether the goat would actually break through the tank, or whether there would be safe areas around the tank, whether the gas inside would ignite. None of that we know. But it's fun because it happens fast enough for us to play with. Now, simulation is also useful in non-interactive media, that film and even static images can be made much more quickly and attractively by having simulations that fill in the details. In these cases, obviously, speed is not as important as with the video games, and accuracy is not as important as in the scientific ones. What's important is that after it's run, you get an attractive-looking piece of work coming out the other end. So this is a clip from Sintel, a short 3D animated movie. So in this very brief clip, you can see fire and smoke coming up around the pot. You can see the sway of the fabric of the characters. And in this clip, you can see the fire breath of the dragon. In traditional animation, every part of these scenes would be drawn by hand. Essentially, the animators would simulate what fire looks like in their head, and they would painstakingly transcribe that onto every single frame. That allows a lot of artistic control, but it doesn't, but only if you put in the extensive effort to make that happen. Simulation lets you fill in those details a lot quicker while still looking good. Now let's take a look to the future of artistic simulation. A good place to look is SIGGRAPH. This is an annual conference about computer graphics. Now the conference is not specifically about art or simulation, but a lot of it appears. And at this conference you can see the new techniques that are going to be coming up in actual applications in the future. These researchers devised a method to read in a hairstyle from photographs or videos. That you can take an actual actor, get their hair, and then their work will convert that hair, find the properties of it, such that when it moves around, it moves realistically. So you could have an actor that appears in most of the movie, you get their hair in, you make a CG version of them for a particular scene, and you can have their hair still move believably. Now, this particular image is kind of creepy looking because it was made by the researchers who developed the technique, not the artists who are eventually going to be using it. Another fun thing that always happens at SIGGRAPH are water simulations. This one, we've got large-scale splashing liquids. That's actually the title of this paper. You can see how the water flows over terrain, and in a moment, how it flows through the city. And we can also see it in these smaller scale surface tension simulations, where a drop of water makes the column that shoots up from a body of water. Now, an interesting fact about these past two simulations is they are both based on smooth particle hydrodynamics, which is the same method that was used in the galaxy simulations from earlier. The point of this is that these highly detailed animations can be made attractively with far less human effort than traditional animations. Yeah, I like that one too. To some extent, this is making animation more accessible to smaller outfits. That even the famous Pixar studios, their animation department started off as just one guy making short films on their equipment. So simulation techniques are opening animation to more people, which means we're going to see more good simulations. More good animations, but it also means we're going to see more bad animations because we can't simulate the talent to make those good. Another potential application we're seeing now is in historical preservation. This here, the Waco glider, was a glider that was used during the D-Day invasions of World War II. It was built primarily out of wood and fabric and was designed to be disposable, that it would be glided behind enemy lines, they would land them in rough, unprepared areas, and the gliders would be basically abandoned while its crew goes on a mission. As a result, only about 20 of these planes still exist today. There was a team of people who, using the original design drawings and 3D scans of an actual glider, one of the few remaining gliders, they produced a 3D model here. And the simulation part comes in, is that they use their model in order to simulate those landings. That people now can recreate those same landings in a computer that were performed on D-Day. So think about that. 70 years ago, maybe a few hundred people performed this task. And today, we can now do the same thing. We can have that same experience that they had. And everyone after us will be able to share that experience too. A little closer to the present are automobiles. That every year older models become harder to find, and there are newer models or fancier models like the ones shown here that you and I are never going to get a chance to drive. But Gran Turismo, a video game that's focused on simulation of car driving, is able to preserve these. That as the future goes on and our current models become less available, or as electric motors and self-driving cars take over from the gasoline powered ones we're familiar with, people will eventually lose those experiences that we take for granted. And video games like Gran Turismo, as long as they stay playable, people after us will be able to know what our experience with cars were like. Another neat thing that's currently in progress is brain simulation. This here is the Open Worm project, an important project. They're making a full cellular level model of a nematode worm. It's a tiny creature and very well studied. It has fewer than 1,000 cells and just 302 of those are neurons, one of the simplest brains that exists. This allows for complete simulation of the worm and its interaction with its environment. Once complete, this could act as the base for simulation of larger scale animals, eventually even moving up to humans. Interesting fact, that muscle activity that was just shown there is done by smooth particle hydrodynamics, the same method that was used in fluid simulations and galaxy simulations earlier. I was amazed at how versatile this one is. Back on track. So, back to spawn. I don't know how many of you heard because of that noise, but I'll talk about it again. So at the University of Waterloo, they are working on Spawn, a human brain simulation. It has only 2.5 million neurons right now, which is a far cry from the 85 billion that humans have. It's 34,000 times short. But it can already demonstrate certain human tasks. It can remember a list of numbers and repeat it back. Very simple job. But what's very interesting about it is that it also has human-like failures, that when the list of numbers becomes longer, it has trouble repeating. So here it uses simulated eye, simulated arm as output. It fed the list of numbers in, which you can see in the upper right bubble. And look at that, the number 8 gradually fades out of its memory, and it has trouble keeping that all straight when it has all the other numbers coming in. So once it gets to repeating the numbers at the number 8, it draws a single line through to indicate that it's forgotten. Now, the gap to full human brain simulation is very large, 34,000 times. But I am confident that one day it will be done. Now, if brain simulation capacity can keep up with Moore's law, where it doubles every 2 years, then we should be able to reach full human brain simulation within about 30 years, before 2050. Now, there are probably going to be some sort of other details and issues that we find along the way that are needed to make a full simulation. But it's simulation that's going to let us know what those limitations are, what those extra features are. Now, if we can simulate one full human brain, then one that can think and feel indistinguishably from the way we do, then perhaps we could simulate more of them, even say a whole planet full of human brains. And then we have to ask, is that happening to us right now? Not like the Matrix where it's a bunch of real people trapped in a simulation, or rather simulated people inside a simulation. It's been argued that if one day we have the capacity to do full planet simulations, and one day we have the interest in doing that, we could very well end up with more simulated people in the world than there are real people. And if that happens, then there is a better than even chance that all of us are in one of those simulations right now. Now, being humans, all of us deserve human rights, like not being unexpectedly killed. And we could be simulations. So doesn't that mean that human simulations also deserve human rights, like not having their computer unexpectedly shut off and taken with it? And if they do deserve human rights, then simulated minds similar to humans but different might also deserve human rights. And that raises an important question of how much complexity must be in a simulated intelligence before it deserves rights, before it becomes a person. So if you play The Sims and you set everybody on fire, the police aren't going to kick in your door for being a murderer. We don't consider The Sims to be real humans. If you imagine a person in your mind in terrible pain, you're simulating that person in your mind, but no one blames you for it. But I'm not going to delve into philosophy any further. Let's get back to the future simulation. Or perhaps let's take a moment to talk about what's not in the future of simulation. What are the limitations that we're not going to be able to overcome? The obvious limit is computer power. Any model needs a certain level of detail to produce accurate results. So the pieces that it's broken into might need to be broken smaller and smaller. Now, a lot of those simulations happen in 3 dimensions. And what that means is if you make your piece smaller, then you increase your number of pieces by the cube of that change. So if you take your element and you cut it in half, you now have not twice as many elements, but 8 times. If you decide you want your time step to be cut in half, you you now have 16 times as many elements. If you want to do an optimization, you add one parameter, you've got 32 elements. You add another parameter at 64, you add a few more, and soon you realize you've got an exponential problem on your hands. And those aren't easy to deal with. Now, so far, computer power has been growing at an exponential rate as well. If we're lucky, Moore's law will stay in place and will continue doubling our computing power every 2 years. But there are some signs that we're running up against the limits of physics. Now, even if we do manage to keep computer power growing exponentially, then we can only keep up with our exponential simulation problem. That is, every time computer power doubles, we get one step further in the exponential simulation. We're still not getting through this very quickly. We also run into trouble with problems that aren't consistent enough to be simulated. In my line of work, metal fatigue is a big problem. That's when you take a piece of metal, you put a small amount of stress through it, not enough to break it, but by doing it back and forth long enough, it eventually does break. You can probably play with paper clips when you bend them back and forth, eventually they break. That's the same phenomenon. Now, metal fatigue depends on, or the time it takes for the metal to break from fatigue, depends on a million things that we can't measure. From the exact arrangement of the atoms inside the metal to the exact temperatures that it goes through. And there are probably a few parameters we don't even know about right now. As a result, metal fatigue can only be analyzed statistically. There are a few ways to do statistical simulations. Monte Carlo simulations are one of the important ones. But even then, you have to simulate over and over with random variables and see what the results, how the results distribute themselves. And that brings you back to the problem before of an exploding number of potential options for your simulation. If we want to be able to simulate metal fatigue more accurately, we're going to need a better understanding of how it happens in order to get that prediction. Another issue is weather prediction. Broad trends in climate can be predicted, but day-to-day weather is a chaotic process. And a chaotic process is not going to be easy to simulate. That if you have that butterfly that everyone likes to talk about on the other side of the world, when it flaps its wings, that chain bubbles up and becomes large enough for us to notice. So if you want to simulate day-to-day weather, if you don't include that butterfly, you've got the wrong answers. As a result, no amount of computing power is ever going to make a 7-day forecast accurate. So there's the disappointing stuff. Let's get back to the future of simulation. One thing that I'm hoping to see in the future is more of an intersection between the art and engineering simulation. For example, I'd like to see kinetic sculptures that are pushed to their limits with simulation and optimization to make them go as fast and be as strong as they possibly can. Now, maybe that's just something I want to work on, but I really like to see it happen. Another thing is that simulations can produce lots of data, most and important insights with those data. Those insights are usually only accessible to the very technical people who created the simulations. Now, art is an excellent way to communicate complex ideas intuitively. I think that maybe we'll be able to see art that attempts to communicate important results like that in a way that is broadly understandable. Along that line, there is a movement in the engineering world of democratization of simulation. That is, up until now, simulations have been done almost exclusively by experts in the field. But software developers of those simulation software, are trying to make it more accessible to a broader audience. But when making the hard decisions that determine how a simulation is made, you need an expert. But there are many cases where instead of making hard decisions, you can just throw more computer power. Since we are having this growth in computer power, there are more of these problems that we can open up broadly because those hard decisions can be sidestepped. As a result, interfaces are getting easier. In fact, there are simulations apps that you can get on phones. And relatedly, as simulations and then push the actual number crunching off to a giant supercomputer somewhere. So all of you in the audience could be performing simulations right now, and in the future it's quite possible you will be. Now on the other end of the scale, more complex simulations are helping to drive newer technology and better designs. For the first time, we're starting to get detailed simulations of electric motors. They're very complicated simulations because they combine electricity, magnetism, heat, and mechanical properties all at the same time. And so we're starting to be able to optimize them and make electric motors more capable. In the past, we would sort of take electric motors for granted, but now, as they get better, we can use them to drive new technologies like electric cars that we're starting to see. That's everything that I have to tell you today. I hope I've convinced you just how much of an impact the world of simulation has on the real world. I hope that when you see a work of art, you'll think that everything could have been handcrafted, or maybe some of it could be filled with a simulation. And next time you have a problem in art or design, I hope you think about cleaning it up. And